All right, welcome to the remaining word problem solutions for optimization. For the sake of quality, I've gone with pre-done solutions. That stylus in the last two videos was really irking me. I'll try to get used to it, but I'm trying a couple different methods here, so I'll be uncovering. Let's start with number 5. This is a Roman window. Builder wants to build a window with a rectangle and a semicircular cap on the top and bottom. Okay, as you see here in the diagram, we have a fixed perimeter. The perimeter is going to be half of a 2 pi r, that's half a circumference, then another half of a 2 pi r, another half of a circumference. We get the whole circumference in total, plus 2 y lengths, those are my vertical pieces here and here. Now we're trying to optimize the area, which is length times width. Here it's going to be 2r for the bottom of the rectangle, and half of pi r squared and another half of pi r squared, giving us a full pi r squared because it's a whole circle in total. Our substitution there, we simplify that area. I'm going to get rid of y here. And so with that perimeter constraint being 30, y equals 30 minus 2 pi r over 2, simplified to a 15 minus pi r, and that's what's going to come in right here. So the area equals 2r times the 15 minus pi r plus pi r squared. Okay. So we distribute, we get a polynomial. Altogether we have 30r minus pi r squared. We take the derivative, we end up with 30 minus 2 pi r. Setting that equal to 0, we're going to get 2 pi r equals 30, r equals 30 over 2 pi, or a 15 over pi. And that 15 over pi is a maximum. Let's get rid of some of these boxes. We know that for a couple of reasons. Obviously, we can do a first derivative test like we're used to. If this were something that had more constraints, we might find a closed interval and use a closed interval method. Second derivative test, or even the explanation of your knowledge of the function, that's really what the second derivative test does. Something like if I go back to my original right here, 30r minus pi r squared, well, that is a reflected or inverted, it's a concave down parabola, so the critical number at the vertex is a maximum. Okay. But, interestingly enough, when we plug in 15 over pi for r to find the corresponding y value, y goes to 0. So it doesn't really look like the normal window, and we actually have a completely circular window to optimize the area. Alright, next, number 6, we have another wire sculptor problem. We have 4 feet of wire. We're going to cut off x and use it for the square. That makes a quarter of x each side of the square. What's left from the 4 feet is 4 minus x. We're going to use that for the circle, which means 2 pi r, the circumference of the circle, is going to be 4 minus x. We're going to do a little substitution here for x or r. Ultimately, you can choose whichever one you want to find first. Doesn't really matter. And we're trying to optimize, again, maximum total area. Okay. Here we go. Area in total would be x over 4 quantity squared, so that's x squared over 16, and then the area of a circle, pi r squared. You choose to make whatever substitution you want, whichever variable you want to solve first. I believe I'm going to bring in all x's, so I've written my area formula a of x. Okay. And then getting rid of r, you see I've used the quotient 4 minus x over 2 pi. It's quantity squared. You were going to have to square either way you made the substitution. This one just has the extra denominator, but I don't mind foiling this. And one of the pi's is going to cancel anyway, so you'll see that in a moment. Foiling that out, I have 2 pi quantity squared. It's going to square the 2 and the pi. 4 pi squared. Here's one of the pi's is going to cancel out. And then for that numerator, just move it over here to the right. 16 minus 8x plus x squared. That's the expanded perfect square. Get out of the way. All right. So now after canceling those pi's, I have that 1 over 4 pi. That's just a constant multiple. I'm going to leave it out front. We take the derivative, and piece by piece, we have a power rule here. Okay, you can see. Let's bring this in. A prime of x. This was the 2x over 16 becoming 1 over 8. It's already reduced. I could have left that 2 over 16 there. You would have seen it. The 1 over 4 pi, I don't need to take that derivative, it's just a constant multiple. And then the derivative of the trinomial here, 16 is a 0. It's a negative 8, don't lose that sign, plus 2x there. Okay, here I am back with my derivative. There it is again, setting equal to 0, finding critical numbers. I've chosen to distribute this into separate terms. You can see the 8 over the 4 cancels out. There's a negative 2 here. 2 goes into the 4. 2 remains in the bottom. Setting it equal to 0, follow these steps. I just moved the constant over. Factor out the x that was common in the first and the third term. Okay. And the next step I'm going to do, a little bit hard to follow, is I'm going to get rid of these fractions by multiplying through by the LCD. We're going to distribute that down both sides. It's an 8 pi. 8 pi times the 2 over pi. The pi is canceled, I get a 16. On the right-hand side of the equation, distributing this 8 pi again into just this first factor. Well, it's first reading right to left. 8's cancel out, leaving me a pi. 2 pi goes into the 8 pi 4 times. Okay, dividing through by that pi plus 4. I get x equals 16 over pi plus 4, approximately 2.24. You're probably getting used to this, but through a first derivative test, we find out that, wait a minute, this is a local minimum. That's not our answer. You know, it was a quadratic with a leading coefficient greater than 0, so we know it was going to be concave up like the parent function x squared, and so this critical number is not going to help us out. So what do we have to do then? Well, how about the domain for x? What was the feasible domain? It was 0 to 4. 0 gives me 4 over pi units squared for a total area. Okay, that's feet squared. That would be no circle, no square, circle only. If I don't cut anything off and put everything in to the circle. If I make x be 4, that doesn't leave anything for the circle. That would be the square only, but then the sides would be 1 by 1. We end up with 1 foot squared. So 4 over pi. That's the greatest area we can come up with. That's when we let x equal 0. Okay, so no wire should be used for the square to maximize area. Alright, taking a look at number 8, we have another printer issue. We want to find the largest printed area given a certain square inches of paper. We can use 200 square inches of paper. That given area is going to be our constraint, and that is h times w given this picture here. They've already marked up the variables h and w. Okay. That being said, we also see a formula for the area of the printed region, and that is h minus 2 for the top margin, 1.5 inches for the bottom margin, and on the width side, we're taking an inch from each side, so that's minus 2. We want to get that in terms of one variable, right? So that h minus 3 times w minus 2, we're going to have to, 3.5, it was. 3 minus 2, pick a variable. I've chosen to solve that 200 equals h times w. For w, I'm going to get rid of w and plug in a 200 over h. Let's scroll this up. Alright, so my area, now this is on my printed region, in terms of h. I'm going to FOIL this binomial. We're going to have to see the h's cancel out when I go first. Product is 200. The outer product, negative 2. The inner product, 3.5 200 is a negative 700 over h. And then my last, the negative times the negative, is a positive 7. So I have a constant 7 at the end, a constant 200 here in front. We can clean that up before we go to a derivative, even maybe put this h to the negative 1, bring that to the numerator. Okay. 207 minus 2h minus 700h to the negative 1. That's my optimization equation, ready to take a derivative. The derivative is 0 for that 207, negative 2, now h to the 0, this stays a constant, plus the negative times the negative coming down, 700, and then h would go to the negative 2 power. I've moved it to the denominator already. Setting that equals 0, besides h being 0, for that undefined point, I'm going to move the negative over. See that negative 2 come to the left-hand side becomes a positive 2. I put it over 1 so that I can have a proportion. Sometimes these diagonal swaps allow for a quicker solution than just cross-multiplying, okay? Or separate steps for multiplying and dividing. Here, that swap gives me 700 over 2, and I have h squared equals 300, h equaling the square root of 350. You can simplify that to a 5 radical 14, but for all intents and purposes, the decimal is going to be good. 18.708 and some change there. Okay. I'm not going to go through all of the verification here. Obviously, a first derivative test is what we're commonly using. We do need to find the other variable w now. W was a 200 over h, plugging in that 350. That 5 radical 14 may be helpful to get to this simplified version, but it's 20 radical 14 over 7, or approximately as a decimal then, a little bit more than 10.69. Alright, number 9. Number 9 is by far probably the most complicated problem, definitely confusing for some of you. We're going to take it piece by piece just in the setup. It has the longest setup. Okay, we want to smuggle precious metals. We're going to take some sheet of some thickness of a precious metal, and we are going to change them into cylinders. Okay, we don't really know what that thickness is of the sheet. It doesn't really matter, but we have two different constraints here, or equations we're going to use. Really, there's only actually one constraint, but formulas you need to go look up for a cylinder: volume, pi r squared times height, right? That's units cubed, so we have two different rates. The cost of shipping is per cubic foot, so volume has to do with our cost. And then how much money we're going to make when we sell this thing, okay, after we deconstruct our cylinders, take those things apart, we're going to sell it for $8 per square foot when it's back in sheet form, I guess. So surface area, how much would it take to wrap that cylinder, right? 2 pi r squared, that's 2 circles, one for each the top and bottom. 2 pi r times h. In the last video with the Beanie Weenies can, we talked about lateral area, but it's circumference times h, and that's units squared. So there's actually 3 components to get that total area. Now you got to read carefully. The height is equal to twice the diameter. H equals 2d. which is 4r. That's the substitution we're going to use in our equation. So what is that equation if all this is happening? Well, we're asked to optimize profit. Normally it's a cost, right? Find the cheapest can or the cheapest fence that will get the job done. But we don't want to minimize cost here. Okay? We want to optimize profit. So the structure of our whole equation, profit, is like your income. What money is coming in, what money is outgoing, and what's the difference, right? Revenue minus expenses. Okay? That being taken into consideration then with the given information, you have to set up your problem this way. You need $8 times the surface area, because this is what we're going to sell it for. We're going to get $8 for the square feet. We're going to subtract what it costs us to ship it, $7 per the cubic foot. So 8 times the surface area, 7 times the volume, subtracting them in between. That is my profit equation. I'll substitute in those formulas on the next slide, and we'll get into the derivative. After 3 minutes just talking about the setup for that problem, getting into it is much easier now, I hope, for you to understand it. Our profit in terms of R is going to be 8 times 2 pi r squared plus 2 pi r h, oh, that's not in R, minus 7 pi r squared h, that's not in terms of R. Remember, h is the same as 4r for a substitution here. I'm going to distribute that 8. We get 16 pi r squared, a 16 pi r times 4r, minus 7 pi r squared times another 4r. Overall, we have an 80 pi r squared minus 28 pi r cubed. It cleaned up to a very simple polynomial. Okay, and taking a closer look at this right now, understand that this is a cubic function, and it's a negative a coefficient there. Okay, negative a coefficient. Let's just get a sneak peek at something like that. It's kind of like this. It came down from positive infinity, bumps up. And I know it goes through 0, 0 because each term has an r factor. There's no like vertical shift. We've lost a couple possible terms here. And so 0, 0, there's a root there. That's one critical number. The second critical number is going to be my maximum. And so just knowing the function in terms of r, my y-axis is my profit, I know what to expect moving forward. So I take the derivative. It's an easy derivative, power rule. 160 pi r minus 84 pi r squared. That's p prime. And setting that equal to 0, I get 4 pi r times the quantity 40 minus 21r. So there's the 0 factor coming in. That one's really straightforward, right? R equals 0 is a critical number. The next critical number comes from 40 minus 21r equaling 0. So r equals 40 21sts. Okay, that's almost 2, but not quite 2. It's like a 1.9 or something there. There's more decimals. You can be more precise. But I'm okay with that. And just grabbing over here. We do want to know what the actual profit is going to be. So when I plug it into the equation, we find out that the profit for each cylinder we make and smuggle of this precious metal is $303.95. All right, I'm going to rush through these last two slides. They're easier, pretty straightforward problems, and I'm trying to make this total video under 20 minutes. So here's a farmer problem building an enclosure along a river, so he doesn't need fence on this side. My vertical pieces are Y on each side with X above. And I know that I have 1,800 feet of fencing total, so my X plus 2Y equals 18 for my constraint and secondary information. My area in terms of, I'm going to make it a Y variable, Normally it's just length times width, so x times y, but using a substitution from above here, x is going to be 1800 minus 2y. So here's the 1800 minus 2y times y, distribute it, and we have 1800y minus 2y squared. Okay. Taking the derivative, 1800 minus 4y, setting it equal to 0 is a polynomial. It's always defined. 4y equals 1800. Y is going to be 450. Now I know that y is my independent variable and my area is my output. So this original shape, you see before the derivative, a of y was a negative 2y squared. That negative a value gives me a concave down parabola. That negative b over 2a was going to give me that critical number, the vertex. Okay, so I know that's going to be a maximum at y equals 450. Back up to here, 2 450s is 900 used up at the fence. It leaves 900 feet left for x. Last thing to do here before moving on, why don't we give some units. Both of those should be in feet. All right, last one. All right, here in number 12, I have a numbers question. This one does give us a constraint early on that they have to be positive numbers. They give us a product of 400 and whose sum is a minimum. Okay, support your answer mathematically. Well, the product is a times b equals 400. The sum is a plus b. And so if I make my sum in terms of a, what is my b relationship but 400 over a? 400 over a is my substitution. So S of a is a plus 400a to the negative 1. And if we take the derivative, the coefficient for a was 1 minus 400a to the negative 2, bringing a squared to the denominator. That's how I'm going to solve. I'm going to move my negative fraction to the left. So 400 over a squared equals 1 as I try to find this critical number. And a squared equals 400. When you take the square root, right, we should get plus or minus the 20. But it was defined as a positive number, so a equals 20. Finding b, 400 over 20 is 20. So 20 by 20, or 20 and 20, are the two numbers. They do ask us to justify our answer mathematically. So we can do that a couple different ways. Remember your first derivative test. At the very least. So I'm going to use this interval. I mean, technically we have all real numbers except for 0 for a domain of our first derivative. But that critical number at 20, I'm going to choose numbers to the left or right. Because they asked us for positive numbers, I'm not going to use 0. Can't divide by 0 anyway and evaluate that. So 1 is going to work. Maybe a 30, something I could square pretty easily. Those are my test values. What is my value of those test values in the first derivative? At 1, I get 1 minus 400 over 1, so that's a negative 399. Obviously, we get 0 for the horizontal tangent line at 20, and at 300, I get 1 minus 400 over 900, so that's 1 minus 4/9 when I reduce. The 1 becomes 9/9, and you end up with 5/9. But you see you end up with a negative value and a positive value. We go from decreasing to increasing. And so we know we have the local minimum for our sum at a equals 20. So there we've justified this conclusion, well, that conclusion. And we should do that whenever they ask for it, even beforehand. You don't want to waste time going into what the other numbers are or the other dimensions are if you're not certain. Remember, we had a couple scenarios where that critical number was actually the opposite. It was a maximum, we wanted a min. I hope you enjoyed these videos, were able to pause as you needed, and you can tell that I'm still not such a fan of the stylus as far as the neatness, but I did like pre-making the slides with the solutions and then being able to go through them. So I'll be happy to make more of these videos going forward. Okay, that's optimization. Test next week.